In this video, I want to talk about how to calculate the work done by a constant force. So let's say if you have a box, and if you apply a force on the box, let's say in the x direction, and its displacement is along the x direction, is the work done by this force, is it positive or negative? Whenever the force and displacement are in the same direction, the work done by that force is positive. Now, let's say if we have a box where it's moving towards the left, but we apply force on the right, what's going to happen? The work done by this force is now negative because the force and displacement vectors are anti-parallel. The force is positive because it's in the positive x direction, but the displacement is negative. So if you multiply a positive by a negative value, you will get a negative result. Now, when the work done by a force is positive, the kinetic energy of the object increases. The object speeds up. In the second example, the object is moving to the left, but it feels an acceleration towards the right. Force and acceleration have the same direction. And so if you're moving to the left but accelerate towards the right, then the object is slowing down. So therefore, the kinetic energy decreases. So anytime work is positive, the object speeds up. And when it's negative, the object, it slows down. The speed decreases. Now let's say this is the ground level, and there's a ball. And the ball is falling due to the force of gravity that is acting on the ball. So it's also moving in this direction. It has the displacement in a negative y direction. So the work done on the ball, is it positive or is it negative? Now the force of gravity is in a negative y direction, so it's negative. And the displacement is in a negative y direction. Work is equal to force times displacement, especially when these two are parallel. So we have two negative values, therefore we should expect that the work done on the ball is positive. Now whenever the work done on an object is positive, what's going to happen to the speed? Anytime the work done is positive, the speed increases. And if you drop a ball from the top of a building, it's going to fall down faster and faster and faster. If you ignore the effects of air resistance, the speed will continue to increase. Now the velocity is negative, and it's becoming more negative, but speed is always positive, so the speed goes up, which means the kinetic energy of the ball increases. So we can say the work done on the ball is positive because it increases the kinetic energy of the ball. So we see that an object that is falling towards Earth, the work done by the gravitational force on the object is positive because the object is speeding up towards the Earth. But let's say if we throw an object up, so it's moving in a positive y direction, but it still has the force of gravity in a negative y direction. What happens? So when you throw a ball upward while it's moving upward against the force of gravity, the work done has to be negative, the work done on the ball. The force of gravity is still negative, but the displacement is positive. So if you multiply these two, you get a negative result. And while the ball is going up, the speed of the ball decreases. And so the kinetic energy is decreasing while it's going up. And then eventually, the ball is going to reach a maximum height, and then it's going to begin to fall. And when it falls, the work done by gravity is positive now, since force and displacement are in the same direction, and the object begins to speed up as it falls back to the ground. And so the kinetic energy is increasing when it falls back down. Now let's move on to circular motion. So let's say this is the Earth, and this is, let's say that's the moon. And so the moon is in orbit around the Earth. Now the Earth exerts a gravitational force on the moon that accelerates it towards the Earth. So does this force exert any work on the moon? Or does it do any work on the moon? That's what I meant to say. So the force of gravity on the moon, does it do any work on the moon? What would you say? Now the moon is moving in this direction. It has a displacement in the positive y direction and a force in the negative x direction. So the combination of these two, the moon is going to turn instead of going straight up or towards the left. So the moon remains in orbit around the Earth. Now, because the force and displacement vector are perpendicular, no work is done. The work done is zero. In fact, work is equal to force times displacement times the cosine of the angle between them. So the angle theta is 90, and cosine 90 is equal to 0. So whenever the force and displacement vectors are perpendicular, no work is done. So since gravity does no work on the moon is going to remain in orbit. Now, if gravity was doing work on the moon would eventually accelerate towards the Earth. For any satellite that falls towards the Earth, the work done on that satellite is positive. As it falls towards the Earth, the speed will increase, and so its kinetic energy will go up. Now, if a satellite is moving fast enough where it can escape Earth's gravity, as it moves away from the Earth, it's going to slow down. And so the work done will be negative because the speed is decreasing. Now, to illustrate this, let's draw it on a horizontal surface so I can compare everything. So let's say this is the ground, which is the surface of the Earth. Now, let's say if we have a ball. If the ball falls towards the Earth, we said the work done is positive. We have a force of gravity that is directed in the negative y direction, and if the displacement is in the same direction, then the work done is positive. Now, the second thing that the ball can do is, instead of falling down, it can go straight. This is basically what the moon is doing. The moon is not falling towards the Earth and is not moving away from the Earth. It's maintaining its orbit. So we have a force that directs it towards the Earth, and it's moving in the x direction. So the moon is going to follow the curvature of the Earth. But whenever force and displacement are perpendicular, no work is done. So the object continues to move at constant speed. Here, the speed is increasing, and so there's an increase in kinetic energy. Here, the change in kinetic energy is the same because the speed is constant. Now, if we have a ball that moves away from the Earth, so basically it's going up, the work done is negative. You have an upward displacement and a downward force. And so as it moves away from the Earth, it's going to slow down. So this is equivalent to throwing a ball up. When you throw a ball up, it slows down until it reaches its maximum height. So the work done for any object that's moving away from the Earth is negative, but if it moves towards the Earth, it's positive. If it stays leveled or in orbit around the Earth, the work done is zero. Now let's focus on this question. How much work is done by a horizontal force of 150 newtons that acts on a crate for a distance of 10 meters? So let's draw a picture. So let's say if we have a crate and we're applying a horizontal force of 150 newtons. And let's say the crate moves with a displacement of positive 10 meters towards the right. Now, because the force and displacement vectors are in the same direction, the work done by this force is going to be positive. So work is going to be force times displacement and multiplied by cosine theta. So between these two vectors, the angle between them is 0. So we have the force of 150, the displacement of 10, times cosine of 0 degrees. So cosine 0 is 1. So it's 150 times 10. So it's 1500 joules. That's the unit for work. So the work done by the force is 1500 joules. Now, what about part B? How much work is done on the crate across a frictionless surface? If there's no friction, the work done on the crate is going to be 1500 joules, because the crate is going to receive the 1500 joules that was transferred to it by a force. A force is capable of transferring energy to an object. So when we say how much work is done by the force, it's 1500 joules. Now the work done on the crate is also 1500 because it receives it. If there's no friction, the crate will begin to speed up, and so the kinetic energy of the crate will increase. Now what about part C? How much work is done on the crate if the crate returns to rest due to friction? So imagine pushing a box across the surface, and then eventually the box comes to rest. How much work did you do on the crate or on the box? In this case, the net work is zero, because initially you increased the speed, but if its speed returned back to zero, its kinetic energy is zero. So there was no change in kinetic energy. So for part C, the work done on a crate is going to be zero. And let me explain why. So we have a force of 150 newtons. So the work done by that force is 1500 joules. Now, if the crate goes to rest, that means there's a frictional force that's acting on it. And so the energy that was transferred by the force was eventually transferred to friction, because friction brought it back down to rest. So the work done by the frictional force is negative 1500 joules. It's negative because the frictional force is opposite to the direction of the displacement vector. And also, friction tends to slow things down. It tends to decrease the kinetic energy of an object as opposed to increasing it. So the net work done on the crate is the sum of the work done by the force plus the work done by the frictional force. So it's going to be positive 1500 plus negative 1500. So the work done, the net work done on the crate is zero. All of the energy that was transferred by the force was eventually transferred to friction, which was lost due to the thermal energy. Friction generates heat. It generates thermal energy. So all of the energy that the force exerted, or that the force transferred to, was eventually transferred to friction, which eventually was converted to heat. So there was no net work done on the crate. And the net work done on the object is equal to the change in the kinetic energy of the object. So if the object returns to rest, its initial speed is the same as the final speed, it's zero, which means the change in kinetic energy is zero. So the net work done is going to be zero. So if you need to determine the sign of work, if you want to determine if it's positive, negative, or zero, there's two ways to do it. First, compare the force and the displacement vector. If the force and displacement vector are in the same direction, the work done is positive. If they're in opposite directions, the work done is negative. And if they're perpendicular, no work is done. The second way to determine the sign of work is to look at how it affects the kinetic energy of the object. Does it increase the speed or decrease the speed? So if the kinetic energy increases, the speed increases. So any force that increases the speed of an object is doing positive work on that object. And any force that is decreasing the speed or the kinetic energy of the object is doing negative work on the object. Now, any force that does not affect the speed, so if the change in kinetic energy is zero, I forgot the equal sign, then the speed is constant, so that force is doing no work on the object. So that's the second way to determine the sign of W. Number 2, a 40 kilogram box is pulled 100 meters by a tension force of 200 newtons at 30 degrees above the horizontal to the right. A constant kinetic frictional force of 80 newtons impedes the motion of the box. What is the work done by the tension force? So let's draw a picture. So we have a 40 kilogram box, and it's being pulled to the right by a tension force, and that force is 30 degrees above the horizontal. Now this tension force is 200 newtons and is a constant frictional force that slows it down, and it's 80 newtons. What is the work done by the tension force? Now the tension force has an x component, which we can call Tx. And Tx, it's parallel to the displacement of the box. The box is moving to the right. So the work done by the tension force is equal to the x component of the tension force times the displacement. Because those two are parallel, the angle between them is 0, and cosine 0 is 1. Now Tx is, well, t cosine theta. Now the angle between t and d is not 0. That angle is 30. So thus we have the equation Td cosine theta, or Fd cosine theta. So let's go ahead and calculate it. The tension force is 200. The displacement is 100 meters. And we have an angle of 30 degrees. So it's 200 times 100, which is 20,000, times cosine 30. So I got 17,320.5 joules. So that's how much work the tension force does on the block or the box. Now the work is positive because Tx and d are both in the positive x direction. They're both moving towards the right, so positive work is being done by that force. Now I'm just going to rewrite the answer here so I can focus on part B. So let me go ahead and erase this. Now, what is the work done by friction? The work done by friction is going to be the frictional force multiplied by the displacement. And then you could put cosine theta if you want as well. Now the frictional force has a magnitude of 80 newtons. The displacement is 100 meters. And now the angle between these two, what is it? Now let's say if we have a force and displacement vector. The angle between these two is 0 degrees. Now, what if the displacement is to the right, but if the force is to the left? So what we have is a picture that looks like this. The angle of a straight line is 180. So because those two arrows are anti-parallel, one points to the right, one points to the left, the angle is 180. So this is cosine 180. Cosine 180 is -1. So this becomes -80 times 100. So if you didn't want to bother with the angle, you could just say that this force is going in the negative x direction, so therefore we could say it's a -80. And the answer will be the same. So -80 times 100 is -8,000. So that is the work done by friction. So what is the net work? The net work done on the crate or on the box is going to be the sum of the work done by the tension force plus the work done by friction. And so what we need to do is add these two values. So it's 17,320.5 plus -8,000. So the net work is 9,320.5 joules. Now, the other way in which to calculate the net work is to use the net force equation. And we should get the same answer if we do it. So the net work is equal to the net force times the displacement. Now Tx is a force that's directed towards the right, and then we have the frictional force that impedes it. So in the x direction, the net force is equal to Tx minus the frictional force. And so we have Tx, which is T cosine theta, minus the frictional force. So the frictional force carries a negative sign because it's towards the left, so that's why it's minus the frictional force. So the net work should be 200 cosine 30 minus the frictional force of 80 times 100. So 200 cosine 30, that's 173.2. That's the horizontal force of the tension force. I should say that's the horizontal component of the tension force. That's what I meant to say. And so we need to subtract it by 80, the frictional force. So the net force in the x direction is 93.2 newtons. And then if we multiply that by 100, that's going to give us the net work that's done on the block, which is 9,320.5. So that's another way in which you can calculate the net work done on an object. Just multiply the net force by the displacement, if the net force and the displacement are parallel. If they're not, then you need to take into account the angle that's between them. So anytime you have a force and displacement that are parallel, you could say the work is simply F times d. But if they're not parallel, let's say if they're at an angle, then the work is now Fd cosine theta, where d is the displacement.